Okay, hi everyone. Lots of you today here, very exciting. Welcome to this week's ZUCCMAP talk. Esty is going to be talking about isogeny cryptography. She's right now an exchange student from the University of Waterloo in Canada, so please give her a warm welcome.
Everybody can hear me? Yeah. Okay. I'd like you to imagine a world where there's no privacy on the internet. What would you do different? Would you send those emails? Would you text your friends? Make questionable searches on the internet? The thing is, this is a future that could happen, right? This is not a question of if, it's a question of when. Maybe in 10, maybe in 15 years, but we know that the threat is coming, and if we're not prepared, then our current internet infrastructure, it just won't do, right? Sounds scary, right? So think about it. This is not even a question of individual computing, right? Banking, government, the dark web, cryptocurrencies, all these things, they will be compromised, right? Anything that anyone on the internet can do will be read like an open book. This is the topic of post-quantum cryptography and the risk that we're trying to mitigate, and especially isogeny cryptography. I'll explain what that means. So my name is Esty. Thank you guys for introducing me. Thank you everyone for coming to my talk. Now this is a math-based talk, but if you're an MTech student that got lost here, maybe I'll just like to show you kind of what we're dealing with. So if you go on any website, and I hope this mouse works. Oh, sweet, okay. So say you go on a website, and you can click this icon right here, and you can check if your connection is secure. This is on Google Chrome. I just pulled this up. And if you look deeper at the security characteristics, you'll see all these numbers and letters. So these are the algorithms that we use to encrypt data sent between you and the website host. Right? So things like your IP address and the information from the website. Right? So all of this data is encrypted. Now there are two major categories of cryptography. I'm going to move out of the way. The first is private key cryptography. So this is when you have two parties and they want to communicate and they already share a secret key. They can use this to encrypt their data between each other. Current algorithms we use are called AES, and experts think that we're safe. We're relatively secure there. On the flip side, we have public key cryptography. So what happens when there's two parties and they want to communicate, but they've never met before, and they don't share any common information? All they have access to is an insecure network where there might be eavesdroppers, like on the internet, right? Like when you're on an online checkout at Zara.com, right? You want to type in your credit card information, but you've never met with Zara and say, hey, let's agree on this private number we'll use to communicate. Okay? Now you should be imagining Darth Vader music, if you can hear it. Okay? Quantum computers. These are computers that can perform computations differently from the classical computers that you guys have in your backpacks right now. And the point is that they are really efficient at specific computations, and they excel at solving the specific problems on which the security of current public key cryptography relies on. Right? Now, if you're thinking, how probable is it that we're going to have these machines around to break the internet? Well, let's look at the major actors that are working on developing this technology, right? There's money in this. So this could happen. And it is happening right now in Zurich, IBM. Okay. And as I said before, even 40 years ago, we knew that there were quantum algorithms that could factor large numbers and solve discrete logarithms, meaning that the foundations of our public key cryptography are at risk. So this is what post-quantum cryptography researchers are trying to solve. We're trying to create cryptography that you can implement on your computers right now, but would be quantum safe. Okay? In response to this crisis, the National Institute of Standards and Technology called for a competition, right? Researchers from all around the world gathered and sent in proposals for what could work, right? So the old stuff, not quantum safe. We need to get rid of that. As you can see here, we have a bunch of different areas of mathematics that could be used to make a secure scheme. Maybe you've heard of these: lattice-based cryptography, code-based cryptography, all these kinds of things. Right? The idea is you want to diversify your portfolio. Right? You don't want to put your eggs in one basket. But there's one area that stands out in particular. It's called isogeny-based cryptography. Right? So all of the other areas, in my opinion, they're very technical. So, this isn't working, so we're going to balance it with this parameter. Now we got to fix this. Now this is broken. It's very technical. It's hard to understand, but it does work. On the other hand, isogeny cryptography is very beautiful. It's based on these deep, profound mathematical ideas in number theory and geometry, and they're not quite as technical. The caveat is that there's a very high barrier to entry, right? How many of you are pure mathematicians here? Okay, so a lot. We have the training for it. But even still, if you're not specialized in these areas, then you will have a hard time understanding the terminology. That's what I'm going to try to teach you today. Right? The other problem that I really should mention is that isogeny-based cryptography made it to round 4 of NIST's competition. Right? There was a scheme, it's called SIKE, and it was a fan favorite. I mean, people loved it. It was beautiful. And 2 years ago, it was broken on a classical computer. So you can go on your computer right now, download the code from GitHub, and break the highest security parameter in 20 seconds. It's not very secure, right? Suffice to say that careers were ruined that summer, and my heart was broken. Right? But it is still worthwhile to see what has been done so that we can understand what can be done in the future. Right? So before we dive into the math, and if my math works, yeah, I'd just like to show you a glimpse of perhaps the urgency of our situation right now. So we're in 2024, and NIST has promised us to release a standard for post-quantum safe scheme. Right? I checked the website yesterday. They still only have drafts. So maybe in a year or so, we'll have something workable. Now, estimates on when quantum technology is going to become viable vary, but in Canada, we have a big institute for quantum research, and some experts say that by 2032, there's a 50% chance of being able to break RSA that is used today. So these are the encryption algorithms that you saw on the websites. Others say maybe 2036, right? So 15, 20 years maybe. It doesn't sound so bad. But let me show you just a little example. So way back in 1995, NIST proposed a standard for a hash function called SHA-1. Right? This is standard used in encryption algorithms. In 2001, they updated it. They published SHA-2. Right? Then in 2005, bam, experts found a weakness in SHA-1. They couldn't exactly exploit it, but the algorithms just weren't passing the security proofs anymore. How long do you think it took until SHA-2 was implemented widely? It wasn't until 2017 that browsers stopped accepting, or at least a large majority, like 95%. Right? This is lucky because a few months later, the first real attack was published. Now, I'll let you decide whether it was coincidence that this attack was published just a few months after the fix was implemented. But the point is that it took 16 years from the time that a workable solution was published to the time that it was actually used in the real world. Right? So do you still think that we have enough time? Well, regardless, I'm going to tell you about isogeny cryptography. And depending on time, I'm going to introduce the mathematics necessary to understand the scheme SIKE that was broken. So supersingular isogeny Diffie-Hellman. And then if we have time at the end, I'd like to show you how it was broken. Okay. So to understand isogenies, you really need to understand the foundational object we're working with, which is called an elliptic curve. Some of you may have heard of it. I see smiles. Okay, what's an elliptic curve? Well, at its core is the solution set to this equation, right? You can vary the a and b however you'd like, and you're looking at coordinates x comma y that would fit this equation. You can pretty much always put a quadratic in y and a cubic in x into this Weierstrass equation. Okay. Now, when you see an equation like this, I need you to ask yourself, x and y, what are they elements of, right? Are they integers? Are they real numbers? Are they integers mod p? What space are we working with? Because this will give you completely different mathematics. Right? This is important. Keep it in your head. Okay, here's an example, if you'd like to kind of bounce this. This is if you vary the a. And can I use the blackboard really quickly? If it doesn't, I'll stop the jiggling. So this was in the real numbers, right? You're thinking, what was that solution set an element of? It was in the real numbers. If we're working over the complex numbers, elliptic curves look like tori. So if you embed it into three-dimensional space, it's a donut. Okay, good for visualization. I don't need the blackboard anymore. I'll walk back here. Okay. The most fundamental thing about elliptic curves that makes them beautiful objects to work with is that you can add points together. Okay, how many of you have taken group theory? Sweet, okay. What does it mean to add points? Well, I have my nice red elliptic curves. I have 2 points on it, and I'd like to add them together and produce 1 point on the same elliptic curve. So what does it mean? Like, am I adding the x-coordinates and the y-coordinates together? Well, maybe then I won't land on the same curve. Right? Okay, so I'm going to give you the algorithm, but let's think about what properties might this abstract addition algorithm need to satisfy. Any ideas? Anyone? Are these group theory experts? No? Yeah? Yeah, beautiful. We want 1 plus 2 plus 3 to be the same as 1 plus 2 plus 3, right? Some other ones I'll give you freebies. Maybe we want commutativity, right? 1 plus 2 is the same as 2 plus 1. And then less obvious, we want a 0 element. So it's an element, or point on my elliptic curve. If I add it to any other point, we'll get the point back. And I'd like to undo addition as well, so I want negatives to be in here. Right? If you know the algorithm for making addition work, then this is very obvious to you, but to me, when I first saw this, it blew my mind. Right? So I have these 2 points. They're going to define a line. I'm going to draw that line. And that line is going to intersect my elliptic curve at one other point. And now I'm going to project that point down. The point that I get is going to be my P1 plus P2. And strangely enough, this algorithm will satisfy all of these properties, more or less. Okay? So just to kind of go through some technicalities, here's my elliptic curve. Once I have addition, I can also do multiplication, right? I can do P plus P, which is 2 times P. And in that case, well, I'll draw the tangent line, right? So when I said that a line intersects an elliptic curve in 3 spots, you don't want to count stupid, right? A tangent line intersects it twice. It's 2 points on top of each other. And so on. We get 3p, 4p, 5p, so on. Okay? Okay. One question you might have if you've never seen this before is, well, I said addition has these nice properties. What is 0 on an elliptic curve? So the point that I can add to anything and get back itself. If you play around with that picture, it's a little hard to see. So what we need to do is think about that question again. An elliptic curve is the solution set to this equation. What are x and y elements of? And it turns out the correct answer is to work in projective space, so I'm going to switch to black. Right? Okay, we're in projective space now. Essentially, we want to be working on a sphere instead of a flat plane. Okay, what's a sphere? Well, I gave you two maps of the same thing, right? This is both the Earth. And I chose this map in particular, so it's flat, and it is quite horrible, right? Anyone who's been to Antarctica will tell you that Antarctica doesn't look like that, right? It's way too stretched out. It's not that long. So in reality, what happened is when we were drawing this map on a flat surface, then we took the sphere and we kind of stretched it out, and the point at the bottom that was Antarctica, it got stretched. So you want to be thinking about a sphere as a point plus a plane. This is the big idea of projective space, projective geometry. So I won't go into too much detail, but the point is that I want to draw my elliptic curve at the top, and we see that squiggle, we want to project it down onto that sphere somehow. If you've seen this before, this is called stereographic projection. How am I going to do this? For those interested, right? I'm going to have my sphere. I'm going to draw the elliptic curve above it. And for each point on my elliptic curve, I'll draw a line between the point and the center of the sphere. That line will hit the surface of the sphere. And that will be where that point from above corresponds to downstairs. And I just keep going. And this was hard to animate, but I did it. Okay. So you see that this branch right here, it kind of comes out and it will come out parallel to us, like towards the camera. And so we'll have this line kind of curving until it's parallel, but it won't quite get there because we don't get to infinity. So we get this additional green point when we draw the elliptic curve on a sphere as opposed to a plane. It turns out this is the correct point to call 0. Okay? I'm hand waving here. I don't want to lie to you, but sometimes I have to. Okay. Please work. Hold on. Oh, there we go. Okay. So when we have objects in mathematics, the next question we want to ask is, what are the functions between them? Right? Nice functions. And a function between two elliptic curves, we're going to call that an isogeny. It's a really nice word. It rolls off the tongue. But we want this function to be special. So we wanted to preserve the addition rule that we worked so hard to create. Well, not you, but I did. Right? So it's a group homomorphism. Right? 2 points here, if I map them over here and then add them, that should be the same thing as if I add them here and then map it through. Same thing. And then there's the concept of a dual isogeny, not quite an inverse, but think about it as some way to go back to your original curve. Okay. Once we have maps, well, what I can do is, why don't I take every single elliptic curve I can think of, so vary that A and B that I had in that equation, and I just draw them all out on a plane, right? I draw them all as points. And then I'll draw all the connections between them. Wow. Okay. Now the point is, in this isogeny graph, is that if I start from, say, that red elliptic curve over there, and I compose some maps, and I end up over here, well, if I hide the isogeny between them, if I hide the way that I got there, and I only give you the start and the end points, then it's going to be really hard for you to find out the isogeny that connected them. It looks stupid on this graph, right, because you can see it, but in reality, once you draw it out, this is a very small example, but you can see that these graphs look really random, these isogeny graphs. And we're going to use that to make a cryptography scheme. Okay. Do we have questions so far? Okay, good. Let's just go over here. Okay, so this is for the kind of fanatics of elliptic curve theory. So we covered the group law, right? There's a thing called torsion points in an elliptic curve. So I'm representing it like this when you see the square brackets. This means the points where when I multiply them by m, in that way where I repeat the addition, then I get to 0. And I'm really sorry, but the literature, it abbreviates the 0 as the infinity. That special green point is called infinity. Okay. And we covered isogenies between them as well. So one quick definition that I always forget this is we call the degree of an isogeny to be the size of its kernels. So that is the number of points that an isogeny maps to 0. It's the number of points that it will kill. Okay? So if I give you a really high degree isogeny, like a 1,000 degree isogeny, that means that it kills a lot of points. It kind of squishes down my elliptic curve. Okay. Now here's the question, why am I showing you these elliptic curves and isogenies? Can we start to use them? Okay. Could I use the blackboard again, please? Okay. Thanks. Okay, so now we're going to talk about some cryptography. So I told you that there's an algorithm where two parties, they can come up with this shared secret key without ever having communicated over a secure network, right? They always have eavesdroppers. And I'll kind of show you how to do this. We're going to start with something concrete, public, right? We have Alice and Bob are going to be trying to come up with a shared secret key. What Alice is going to do is she's going to do something secret to this. Right? This is secret, and she's going to publicize what she gets. Bob is going to do the same thing with his own secret. And now they're going to kind of swap what they got. So these two things are going to become public. Alice is going to do her secret thing again. Bob is going to do his secret thing again. And hopefully they end up with something common, and they keep that secret. Right? So I'll give you kind of an example. Let's say if we start with the number 8, Bob does something secret to it, and he comes up with 24. Alice does something secret to it, and comes up with 40. And then these things are public. And then they get 120 in the end. Does anyone see what happened here? Marcus? Okay, beautiful. So this is times 3, and this is times 5. Okay, what's the problem with this? Yeah. Okay, I'll give you a little bit of a, I want you to be a little bit more specific. So I'll tell you that Bob and Alice both multiply by a secret number. Okay, can you tell me what's wrong? Leon? Yeah, exactly. We have division. So whatever Bob did here, so he multiplied by 3, we know how to undo, because I think we can all divide by 3 as well. Okay? Sweet. Okay, so we need some secret functions that are one way. They're easy to do this way, but hard to do the other way. Okay, back to PowerPoint. I really feel powerful right now. Okay. So I'll show you how this is done right now. This is current elliptic curve cryptography. Right? We have Alice and Bob, and what's public is in between, and then the purple here is going to be our shared secret. What we'll do is we'll start with a public elliptic curve E and a point on it. Alice is going to pick some secret number A, Bob is going to pick some secret number B. Alice will compute A times P, and Bob does the same. All right? Then they swap. And then what Alice can do, she takes Bob's B times P and multiplies that by A. So that means B times P plus B times P plus B times P, A times, right? Both of them should end up at AB times P, okay? And the point is that we don't really have a division algorithm here, just like we did with the 8 times 3 equals 24 example. So given this A times P, it's really hard to undo that and get back to what A is, unless you have a quantum computer. Okay, so we're going to do this differently now. We're armed with this machinery with elliptic curves and isogenies. We're going to come up with something better. Okay? Instead of playing around with points, we're going to play around with actual elliptic curves and isogenies between them. For group theory fanatics among you, Alice is going to pick a secret subgroup A, Bob is going to pick a subgroup B. These are going to correspond to kernels. Right? They'll send each other, they'll send each other an abelian group, so an elliptic curve, quotiented by A, and same way back, right? And this is going to kind of commute. So in reality, this scheme with isogenies, what we're going to do is we're going to have like a secret subgroup is the same as a secret kernel, and it turns out that's the same thing as picking a secret isogeny, okay? So pretend we have a starting public curve E. Alice is going to pick a secret isogeny phi of A, and Bob is going to pick a secret isogeny phi of B, okay? Then they swap their outputs, right? The isogeny that they got to in the end. And like I told you, that if you have the starting and ending elliptic curve, it's really hard to find the isogeny between them. So the secret stays secret. Okay? Technicality. Okay. Here's my problem, though. Phi of B is an isogeny from E to E quotient by B. If you don't know what quotienting is, just pretend it's another elliptic curve. Alice sends Bob her output, E quotient by A. And Bob looks at it and he says, well, what the hell am I supposed to do with that, right? My isogeny acts on E, not E quotient A. Okay, so we need to fix this. And the fix that was implemented, this was the genius idea in 2011, was we're going to work in these kind of large torsion spaces. So think of these as kind of the parts of elliptic curves that are easy to understand. In reality, it's the torsion subgroup 2 to the A and 3 to the B for Alice and Bob, respectively. Okay? And we're going to, this is kind of like linear algebra, if you've seen this, right? We can have a basis for each of these really large spaces. So Alice is working with her large space, and it has a basis, and Bob is working with his large space, and it has a basis. These basis elements generate the whole big space. So we need this kind of additional information, and I know the slide is getting very crowded. The main idea is that along with the outputs to the isogenies, Alice and Bob are going to send along these torsion points. Right? So Bob has his giant space over here. Alice is going to tell Bob how her isogeny acts on his space. They're going to swap these additional points. And I don't want to go through this because this is a lot. But in the end, they should be able to recover kind of where the other person was at without revealing too much information. So Bob is going to be able to evaluate some like pseudo 5B isogeny on Alice's output without actually knowing Alice's isogeny. Okay? Okay. So this was the big idea of SIKE, and notice kind of the advancement, the progress is right now we have cryptography that deals with points. And this idea was talking about elliptic curves. It's like the objects we're working with. It's beautiful. Okay. Nobody's asked me what a supersingular elliptic curve means, so I'm not going to tell anyone. And I'll just show you, like, these are kind of these starting elliptic curves that we might be working with, right? So these are very, like, nice, easy to work with objects. You can actually work with these things. Round 2 was updated to be a little bit more efficient. And what parameters are we using here? So for those really large spaces, remember I had that 2 to the A torsion points, 3 to the B torsion points. So we're looking at numbers kind of this form. It's kind of very big. And again, now with this scheme being broken, we can break these security parameters. Okay. Questions? Hi, Benny. I'm going to call you out for being late. Okay, how am I doing on time? 15 minutes. Okay. Can I show you how this thing was broken? Because I think this is what we all came here for, right? Okay. Okay. So here's what we're going to do. So the whole point to breaking this scheme is that there's a public elliptic curve E, and the public elliptic curve E quotient by B, and they're connected by, say, Bob's secret isogeny 5B. Right? And the way that we structured these things, we can actually decompose both Alice and Bob's secret isogenies into, well, say Bob has 3 to the B isogenies, so he'll decompose them into 3 isogenies. So they're like really small isogenies. And if it's a 3 isogeny, that means it has degree 3, so it kills 3 points, right? So this thing kills 3 points, sends it to 0. This one kills 3 points, and so on until we get to E quotient by B, okay? We need to find this 5B in order to be our malicious internet eavesdropper. Okay, how are we going to do this? Well, easiest thing is, at each step, try to guess a 3 isogeny and see if you're right. The only thing is, we need some sort of way to tell us, are we on the right track or not? Because if it's 3 to the B, if you check every single possibility, this is exponential, and that's not going to work. So we need to guess an isogeny and then have some sort of algorithm that'll tell me, okay, I'm on the right track. This is called a decision oracle. If you're a computer scientist, you like those words. Okay. And the right oracle, the right kind of question to ask, am I on the right track, is going to end up, does a certain isogeny of abelian surfaces split? Oh, okay. Abelian surfaces scared me a little when I first saw them, but really they're generalizations of elliptic curves. So you might want to think of this as like an elliptic curve is kind of like a torus, an abelian surface is like a blob with like more holes and like higher dimensional space, essentially higher genus. What I found really cool is just how elliptic curves had this addition rule. We call it a Lie group. Well, abelian surfaces also have an addition rule, but because we're kind of higher degree, instead of drawing lines between points, we're going to draw higher dimensional polynomials between points. And then that'll help us add things together, right? So cubics, quintics, all that, instead of just a line. Okay. So abelian surfaces, essentially there's 2 types of them. These higher dimensional blobs, they look like something really ugly or something really nice. If it's something really nice, then it's a product of elliptic curves, which means it's kind of like an elliptic curve from this side and an elliptic curve from this side as well. Because they're nice, they're very rare. If we're working over a finite field, for example, then there will be that many of them, p squared, right? If finite field over a prime. And the other option is we have something really ugly, right? This is the blob that you need to, okay. We're going to think of them as something very generic and more polite. Okay, I think I scrolled back. Okay. Yeah. Sure. Okay, so just like we had this object called an elliptic curve and we looked at functions between them, group homomorphisms, we might want to look at functions between abelian surfaces. And because there's 2 categories, they're going to have 4 different types of isogenies. Right? So the most generic one, and then if you have something generic and you split it into something nice, we call that a split isogeny, otherwise it's a glue. And then the very, very rare type of isogeny is the nice thing maps to a nice thing. Okay. Now here's the crux. Here's what we're going to do. These researchers that were working on SIKE, they found this theorem from like 1996, I think. It's called Kani's theorem. And it allowed them to create this decision oracle. So they did this by characterizing when an isogeny splits. In other words, okay, we're going to try to take a step. We're going to try to construct out of that. We're going to raise it upstairs to some isogeny of these really complicated, higher genus blobs. And if you took the right step, you're on the right track, then Kani's theorem will tell you that this isogeny splits. And because the splitting isogenies are more rare, right, you have a very high chance of telling yourself, okay, I'm probably on the right track. Okay? This is the thing that I didn't want to show you. Okay. Don't look. You're still looking. Okay. Look at here. Okay. There's just a little bit more detail, and this is kind of what I think most researchers would say is the most surprising thing about this attack. I have my sequence of isogenies of my steps, and I want to figure out what the right steps are. And remember that Bob is working in this large torsion space, and he has a basis for it. Oh, no, we'll call it Alice's, sorry. So Alice's torsion space has a basis, PA and QA. These are 2 points on the elliptic curve. That's kind of the starting point. And under each isogeny, these points get mapped until you get to the end. And remember that the SIKE protocol had these torsion points be public. So the endpoints, the 2 points at the end in yellow are public, and the 2 points in the beginning are public, okay? Everything else pretended secret. What we're going to do, we're going to guess the 3 isogeny, right? We'll guess it, we'll see where we end up. We're going to see E1 question mark is my new elliptic curve. And what I'm going to do is I'm going to construct an isogeny, an auxiliary isogeny, and all we need is this isogeny to be the correct degree. And then everything else will work, right? Using this auxiliary gamma isogeny, we're going to construct a big capital phi. This capital phi is kind of like the upstairs, so this is going to be the map between abelian surfaces, not just elliptic curves. And this capital phi is going to use our auxiliary isogeny and the public points that are at the very end, okay? And the way this works is that if E1 question mark is correct, then, well, E1 is joined to the end by an isogeny. There's an isogeny there. So Kani's theorem will tell us that that thing will split, okay? So that's it. We found the key. So we're going to just find the right step and then keep going. The only difficult thing is constructing this auxiliary isogeny. It turns out to be a little bit of a what is it called, like a cork in a bottle? Yeah. Well, it turns out to be difficult. But the good thing is you only need to do it once because you can repeat these things. What you can do is you can construct an auxiliary isogeny from E of the correct degree. And then as you're guessing along, just keep track of the correct steps. And then use kind of a commutative diagram to get an auxiliary isogeny from your guess to this C, and it will work out. Okay? And you fiddle around with it. As I said, the only difficult thing is constructing this auxiliary isogeny. Once you have that, boom, you can recover the whole path. Questions? We broke it. This is huge news. I mean, the guys who were working on this were trying to make SIKE better. They weren't trying to break it. And it's quite surprising because the theorem that was at the backbone was known 15 years before SIKE was even invented. Right? It's kind of surprising. Okay. So just to wrap up, I'm going to take a step back. First of all, if you're a computer scientist, you might want to check out the code. You can run it if you can do, I think, Linux, and then you can run this. And of course, there's been improvements on this attack. So I gave you the original attack, but this is there's been ways to make it a lot faster. The nice thing is that the whole thing isn't completely broken, right? So there are still secure schemes that are believed to be quantum safe that don't include torsion points, right? This was the big downfall of SIKE, was including extra information. And usually in cryptography, extra information is bad, okay? So I hope that isogeny research will continue, because it's quite interesting. And I hope you learned a little bit today about this very complicated math thing. And thank you for coming.
Thank you so much for this talk. Are there any questions? We have about a little more than 5 minutes for questions, and then for the apéro.
Everyone's trying to save time for the apéro. Yeah?
So maybe this is a bit unrelated to all the math you talked about.
Okay.
On the practical side, you were saying that it took 15 years for browsers to not accept like this Schaubman algorithm and this kind of stuff. So do you know if there's any work on like people automatically using the most up-to-date cryptography schemes so that we don't have to have people manually update their schemes, or is it mostly like people just realizing at some point and just...
Okay, so your question is there work being done right now to keep cryptography up to date? Yeah?
Yeah, or more on the practical side.
More on the practical side. So I'm glad you asked this. I worked at a company last summer called Isera, and their whole business scheme was to create tools for companies to assess their crypto and then give them these new post-quantum algorithms. Obviously, the easiest thing is when a business is starting out to just implement the best standards there could possibly be. But if there's a lot of libraries that are already using old tech, then it might be easier to use that. And we want to kind of prevent that because the costs associated with switching are like 10 times higher than just using things that are secure from the first place. But it is now kind of emerging as a new area where people can make profit off of making sure that people are using the correct quantum safe crypto.
Because I was thinking if we had like one standard library, okay, like everybody just syncing with this one,
Yeah.
we could have like less of this problem.
Yeah, exactly. So that's what NIST is trying to do with having this standard, but they haven't really published it yet, I believe. And things that are already using old tech, it's extra energy and time, resources to get them to switch, right? That's the world. Yeah. Any other questions? I am hungry. Yeah?
One of the first slides, you had this diagram which showed like algorithms which we know are not quantum safe.
Yeah.
Ones which we think are, and ones which were broken on the right.
Mm-hmm.
And the ones that you had in the leftmost column, do we only know of quantum algorithms to break these, or do we also know, like in this case that you just showed, any standard algorithms to break these? Are all of them just breakable with quantum computers?
Wait, you said the category on the left. Do you remember which was that, the not quantum safe ones?
Yeah.
Okay, so the question is, do we know any classical algorithms to break the not quantum safe things? So right now, no. We only know quantum algorithms. So until we have a viable quantum computer, we probably won't be able to break the things that we have now. And I say that because the problems like discrete log and RSA, these things have been around for much longer, right? So say lattices, and isogenies, all these things, they've been developed for like 100 years, but people have been, or hundreds of years, but people have been wondering how to factor large numbers for like thousands. So there's kind of a lot more testing, and because it's so widely implemented, I think there's a lot more interest to try to break it. Unless you use like stupid like textbook RSA, right? Things like that are broken, so they're, you have to be careful anyway. But if you're still using kind of the most up-to-date, not quantum safe algorithms, then you should be good. But there could be. Someone might come around tomorrow and say, hey, I found this algorithm that will factor large numbers without a quantum computer. Okay. Well, thank you guys so much for coming. It's been a real pleasure.